Exponential growth and decay. So things in the real world that tend to grow fast as they grow larger or decrease slower as they get smaller, these types of things are exponential functions. So obviously if they're growing, it's exponential growth, and decay in the case of decreasing. Today we're going to look at both. This is lesson 3. We may get to 4, that's my plan, but we'll see how long it takes. So the first example talks about a rumor and how it spreads. So that rumor, it starts with 3 people. So those are the 3 people that know this to start out. So let's see how this grows. It says, why does it make sense that the number of people who have heard a rumor would grow exponentially? Okay, because obviously the more people that know it, the more people that know it means the more people could spread it. Okay. So let's fill in this table. Okay, so we've got days on top and then the number of people that know it on the bottom. So at day 0, okay, 3 people know it. So, and it says that my key word in here is that it doubles each day. So 3 people start with it, so that's our starting point. That's going to make sense in just a minute. And then all of a sudden 6 people know it because it doubles. So then we've got 12 people on the second day, and then it doubles, so it's 24 people, and then it doubles. Whoops. So then that brings us to 48 people. Okay, you see how this starts to grow pretty rapidly. So 48 people, and then by the 5th day, 96 people know it, just as it's doubling each time. Okay, so it says we'd like to determine the number of people who know the rumor after 20 days. Okay, so the best way to do this is to be able to come up with a formula instead of taking this chart out to day 20. So if we examine this, and at day 0, okay, so now I'm just taking this chart and looking at it in a different way. So at day 0, 3 people know it. Day 1, how many people know it? Well, it's that initial 3 times 2 because we're doubling. So that gives us that 6 people, okay, know it. Now on day 2, we have the number of people that know it is that initially 3 times 2 from the day before times 2 more. So it doubles again. So 3 times 2 times 2, which if we think about our exponents is 3 times 2 squared. Right? And we know that on day 2, 12 people know it. So what about on that 3rd day? So on the 3rd day, we still have the 3 times 2 times 2 from the previous day, but now that amount doubles. So think about that exponentially. It's 3 times 2 to the 3rd power, which gives us that 24 people know it. So now, hopefully you're starting to see a pattern here that the initial amount of people times 2 to the, well, if we went from this back here was 2 to the 1st, then 2 to the 2nd, then 2 to the 3rd. So this one is going to be 2 to the 4th on that 4th day. So that gives us our 48 people if you were to expand this out and multiply this. So then on the 5th day, it's going to be the initial people, 3, times 2 raised to the 5th power. That's going to be 96 people. Okay? So working with this pattern, let's come up with a formula. Okay? For the people who know the rumor N after D days. Okay? So the people that know the rumor N equals, we start off with that initial 3 people times, what's my growth? What is it doing each day? It's doubling, okay, and we noticed as we saw this pattern, it's raised to the number of days. So there's our general formula for this. So now we're able to figure out how many people know this rumor after 20 days. So take a minute, grab your calculator, and come back when you've got it. Okay, so on that calculate page, we want to do 3, whoops, let me just do this quick. There we go. Okay, 3, and then times 2 raised to the 20th power. Okay. Hit enter. All right, so that's how many people know this rumor, okay, after 20 days. If I can find my cursor. No! Lost my cursor. Oh, there it is. Okay, so N equals 3,145,728 people, okay, know this rumor just after 20 days, okay? So it says exponential growth can be very fast. So it says, assuming our equation from B holds, how many days will it take for the number of people knowing the rumor to surpass the population of the United States, okay? And they tell us that the population of the United States is 315 million people. So we know that on day 20, okay, only 3 million, well, I shouldn't say only, 3 million people know this. So I don't know, so let's jump up to day 25. So let's figure out what that is. We've got our formula, so 3 times 2 to the 25th power, and go to your calculator, and you should get now, just 5 days later, okay, 100,663,296. Okay, so that's too small, okay, because notice that population is 315 million. So, I don't know, but the way that it's growing, let's try 26. Okay, so on the 26th day, go to your calculator, and you should see that we end up with 201,326,592. Well, it's still too small there. So, but notice what happened just in one day. So, I don't know, I would keep creeping up. Let's see what happens after 27 days. To the 27th, okay. Again, go to your calculator, and wow, okay, look what's happened here. 184, okay. That is definitely greater than that 315 million, okay. So it would take about 27 days for all the people in the United States to know the rumor if that exponential pattern continued, okay. All right, so go ahead and flip that. We've got this little example of this little gentleman here. His name is Helmut. He's from Finland. He's heading towards this lighthouse in a very peculiar way. It says that he starts 160 feet from the lighthouse, and that's indicated in our diagram. And it says on his first trip, he walks half the distance to the lighthouse. So that's going to be our key piece of information, half the distance. So on his next trip, he walks half of what is left. On the consecutive trips, okay, so every time he takes a trip, he goes half the distance that is left. So let's see how we can model what the distance D that Helmut has remaining to the lighthouse after n trips. So distance D after n trips. So we can start filling out this table. So n trips, so 0 trips. Okay, he hasn't left his starting point. He's at 160. After 1 trip, we said he walks half the distance, so he's got 80 feet left. So now after 2 trips, half the distance, okay, he's got 40 feet, then 20 feet, then 10 feet. So you can see, okay, we're taking half each time. So we're multiplying, okay, by half. So now part B says, each entry in the table could be found by multiplying the previous by that number. So it's important that we always want to think about exponential functions in terms of multiplying. So you may have thought in your head, oh, we're just dividing by 2, which is true. But it's best to think, because once we start to write the formulas, it's best to think about what we're multiplying by. So if you think in your head dividing by 2, think what's the same as multiplying. So dividing by 2 is the same as multiplying by 1/2. Okay. So it says Like we did in exercise 2A, we want to see this process as repeated multiplication of 1/2. So if we can fill out this pattern. So we start out with 160, and then we take 160 and multiply it by half and get 80. And then we take the term before. This is going to start to sound a little bit familiar. We take 80 and multiply it by a half. Or in other words, we take 160 times a half, which was the term before, and multiply it by a half again, and we get 40. And hopefully you're going to start to see a pattern start to evolve here. So if I were to, I'm just going to back this up and write it in exponential notation. So we'd have where we started with times 1/2 to the second power, and that comes out to be 40. And then what about on the third trip? 160 times 1/2, right? That's going to be to the third power, and that becomes 20, okay, or equals 20. And then on that fourth trip, 160 times 1/2 to the fourth, I don't know, randomly know why my highlighter keeps turning on, and we end up with 10. Okay, so we just took what was in that table and represented it sort of as a formula, okay? So we're starting to sketch out what this formula could look like. So it says based on C, oh, look at that, give a formula that predicts the distance D that Hellman has after n trips. So distance D equals, where did he start? What was his starting point? 160 times, and then what was it decreasing by in this case? Okay, we were multiplying by a half, and we raised that half to the number of trips that he was taking. So it says, how far is Hellman from the windmill after 6 trips? Provide a calculation that justifies your answer, and don't forget those units. So what about D of 6? So 160, 1/2, and 6 trips. Okay, so he's now 205 feet from the lighthouse, or that's how much distance he has left to reach the lighthouse. It says, Hellman believes he will reach the windmill after 10 trips. Is he correct? So, D of 10, 160 times 1/2 to the 10th power. Okay, and go right ahead, go to your calculator to do this calculation, and you should end up with 0.15625 feet left. So is he at the windmill yet? So no, he has not reached, okay, a distance of 0. Okay, no, the distance is not 0 yet. No, D does not equal 0 yet. Okay, so it says explain why Hellman will never reach the windmill. Okay, so we're getting a little philosophical here. Okay, because think about it, he's always taking half the distance that's left. Half the distance that is left. Okay, is he ever technically, philosophically, mathematically going to reach that windmill? Okay, no, he's not. Okay, you can always take half of the number that's before. You can always take half, and he's never going to get to 0. You can always take half of something that's left. Okay, so it says, why is the domain of this function only whole numbers? Meaning, okay, 0, 1, 2, and 3. Okay, so the domain is only whole numbers because we're measuring the number of trips. Our domain is the number of trips. Okay, so which is a discrete measurement, okay, one that is unconnected values along the real number line. So he's not taking a third of a trip, okay, he's taking 0 trips, 1 trip, 2 trips, 3 trips, okay, he's not taking part of a trip, all right. All right, so I think we're doing okay. Let's see what we could do with that next lesson. Okay, so exponential functions. So up until this point, that's all we've really been focusing in on is linear functions. So, and linear functions, their biggest characteristic is their constant rate of change. So we just got done looking at exponential growth and decay, which are exponential functions. So let's look and see some characteristics of those exponential functions. Okay, so let's take this function. Let's have a little exercise for our brain here. And it says evaluate this function, okay, for f of 2. So we know the function is 8 times 2 raised to the second power. So going to your calculator, you're going to get 8 times 4, which is 32. So if we express that as a point, okay, my input, or my x, is 2, and my output, or my y, is 32. So let's do the same thing with 0. Okay, so we should end up with that equals 8. So 0, comma 8. All right, this is also known as the y-intercept, okay, of this function. And then what about f of negative 1? So 8 times 2 to the negative 1. All right, let's think about this one. Obviously, go right to your calculator, get an answer, but I want to make sure that we've got that understanding of that negative exponent. Okay, so that's 8 times, remember, when you think negative exponents, think division, which is 1/2. Okay, that's equivalent, okay, to that first there. So what's 1/2 of 8? It's 4. Okay, I just wanted to show the relationship between that 2 to the negative 1 is the same thing as 1 over 2 to the positive 1. So what is that point? Our input is negative 1, and our output, or our y value, is 4. So we're going to use this information to calculate the average rate of change of f over this x interval. So if we recall, okay, from when we talked about rate of change, it's the change in y over the change in the x. Or the way you think about it, y2 minus y1 equals x2 minus x1. I'm going to always use that because it's less writing. So if I want to know my average rate of change, I'm given my x values right here. Okay, so if I think 0 minus a minus 1, and then what were the y's that went with those two x's? Well, we found those up in the exercise right above. So when x was 0, what did we come up with for a y when x was 0? We came up with 8 minus, and then what did we come up with for a y when x was negative 1? It's over here. Our y value is 4. So we end up with 4 over a positive 1. So my rate of change over this domain from negative 1 to 0 is 4. So now they're saying, all right, well, calculate the average rate of change from 0 to 2. So again, my change in y over my change in x. I've got my x's. They just gave me my x's. So from 2 to 0. So 2 minus 0. Well, what was the y that went with an x of 2? Right over here, we calculated it to be 32. Okay, minus, and then what was the x that went with, or excuse me, what was the y that went with an x of 0? And it was 8. So doing that calculation, we get 24 over 2, which comes out to be 12. Okay, so hopefully you're kind of having one of those moments where you're like, this is interesting. So the average rate of change from this interval was 4, but the average rate of change over this interval was 12. It says, what does comparing answers from B and C tell us about this function? Okay, it tells us that this function is not linear. Okay, if you obviously couldn't tell by this, obviously, clearly this is not linear. But what backs it up is it's not linear because it's not a constant rate of change. Okay, that is the linear function's claim to fame, is constant rate of change. Well, the claim to fame for the exponential function is that it's not a constant rate of change. There is a rate of change, but it's certainly not constant. So it says, using your calculator, draw a sketch of this function on the axis in the window indicated. So if we go to our calculator, we want to change, when we graph it, we want to change our values in our window to be this. Okay, so go ahead, graph our function, okay, that 8 times 2 to the x, and change up your window to these values. Okay, so your graph should look like this. And then let's look at our y-intercept. So let's see what this is right here. So we can go to our table. So we know that our y-intercept is where x equals 0. So if I hit Control T, try that once more, Control T, okay, and find and scroll up, okay, so my y-intercept is 8. Okay, so, so when I go to just draw this sketch of this, okay, I'm going to put that y-intercept on there, 8, and, okay, it does something a little bit like this. Okay, it starts to grow rapidly. Okay, so my y-intercept is 8, so keep that in mind, and then maybe take a gander back up at our function. Our y-intercept is 8. Look at that function. F of x equals 8 times 2 to the x. Keep that in mind. Okay, exponential functions are all about multiplication. So what does it look like here? It says a general exponential function has this form. Okay, put this on an index card, where A is the y-intercept and B is the base or the multiplying factor. Okay, B is sometimes known as the growth factor. So A, right there, that's the y-intercept. Okay, and the B, what's raised to the exponent, okay, is that multiplying factor. All right, go ahead and flip it, and let's do a little practice with this, and then we'll wrap it up. Okay, so looking at this function, okay, it says evaluate g of 0. What point does this indicate on the graph of g? So if I do g of 0, 54 times 1/3 to the 0 power. By all means, use your calculator, but use your brain here too. 1/3 to the 0 power. Anything to the 0 power, hopefully you remember, is equal to 1. So this is 54 times 1, which is just 54. So what is this? So 0, 54, that's the y-intercept. Okay. So right there, there's our y-intercept. So you're going to get to a point where you're not even going to have to do that calculation, and you're going to know that that is the y-intercept. Okay? So we can do some more calculation here with g of 1. Okay? And this is going to give us more points on our graph. Okay? So g of 1, that's going to be 18, and then g of 2 is going to give us another point on our graph, 54 times 1/3 to the 2nd power, okay, and that's going to come out to be 6, okay. So we certainly can go ahead and sketch this function, okay. I'm just going to kind of move through it kind of quick here to save a little time. So 54 is my y-intercept, and they want you to sketch this from -10 to 100 on the y-axis, and then from -2 to 4 on your x-axis. So it says, why is this exponential function always decreasing while the one in number 1 was always increasing? So if I go back and look at 1, what was my multiplying factor? My multiplying factor was 2 there. Well, what's my multiplying factor here? My multiplying factor is 1/3. Okay, so what happens? Okay, when your multiplying factor, okay, is greater than 1, okay, it's going to be increasing. Okay, I'm going to draw a little increasing picture. But if your multiplying factor is less than 1, okay, then it's going to be always decreasing. So here's another thing that you could put on an index card. So y equals ab to the x will increase if my multiplying factor is greater than 1. But it will always decrease if my multiplying factor is less than 1. And I should be more specific here. That b is going to be between, okay, 0 and 1. Okay, less than 1, but greater than 0. Because if it were equal to 0, we wouldn't even have an exponential function. Okay, all right. So looking at these really quick, they just want to identify what's the y-intercept and tell whether it's increasing or decreasing. So there's the y-intercept. And looking at my growth factor, 2/3. Is 2/3 greater than 1, or is it in between 0 and 1? So hopefully you know that it's in between 0 and 1, so it's going to be decreasing, and that's the y-intercept. There's the y-intercept. 1.5, okay, that's going to, obviously that's greater than 1, so it's increasing. Y-intercept, and that right there, 3/2, okay, that's 1 and 1/2, so that's also greater than 1, so it's going to be increasing. All right, nice job, guys.